Again, thanks for joining. And so next we're going to start going one level down to really go into a little bit more details about the TVM effort. And to run the show here, I'd like to invite Tianqi Chen, who is a PhD student at the University of Washington and is really the person who sparked the idea and who's really brought us all here together. So welcome, Tianqi.
Thanks, Carlos. Hi, everyone, again. So I'm going to tell you a bit more deeper about what is TVM. So before I do that, let me tell you how it begins. 2 years ago, actually, my friend Thierry here came to me to say, hey, Tianqi, I'm working on this awesome deep learning accelerator, and do you want to work together? I said, sure. How can I get started? How can I put my favorite puppy detector on top of this accelerator? And then he gave me this entire page of microassembly manual on how do you do microassembly coding to program that accelerator. Well, as you can see, that the gap between the high-level frameworks and the low-level hardware is just like the gap between writing Python code and writing microassembly code for this deep learning accelerator. And you can see that that's a really huge gap that we want to really solve. Before we dive into what is our solution to solve this problem, let's take a look at what existing frameworks do. I was fortunate enough to be part of co-creator of this deep learning framework, Wave, and I helped co-create MXNet. So I will tell you what I will attack this problem 2 years ago. If you look at most of existing deep learning frameworks, what you can do is that they will represent their computation in what we call high-level data flow graphs. This is like SQL language for database that allows you to make a declaration of your workload and really throw that to your execution engine. The special part of this high-level data flow graph is that every node in this high-level data flow graph contains primitive tensor operations such as convolution 2D or matrix multiplication. In order to offload this high-level data flow graph onto low-level devices, in this case, NVIDIA GPU, what is happening is that we will need to offload them into low-level libraries like CUDM, which are heavily optimized by a team of engineers in the vendor and on the target device. So if you want to take a closer look at what's really happening, for each of the operator in here, actually there was an underlying specification on implementing those operations. And behind the scene, there was one engineer, actually a team of engineers, trying different implementations. For example, for this transformation application, the first thing we are taught to do is just writing for loops, and that will give you OK speed on the target. If you have learned things about caching structure, maybe you want to do things like transforming your loop so that it gives you better loop locality. And if you want to work on accelerators like Inferenza or Vita, you want to really take benefit of the accelerator intrinsics that the accelerator have to offer to you and map them to the accelerators. So what you can find, what's happening here is that there's a human in behind, or a team of humans that are doing human-based exploration of how to do the code optimization. And that is the state of art today. So what is the limitation of this approach? Well, the fact is that most of existing frameworks are still taking this approach because this is the most obvious thing to do. But the problem is that for each of the high-level operator in the computational graph, they have to be supported by a low-level library like CUDM. As you know that machine learning or deep learning is a fast-evolving field, there is always new workloads and new operators coming in. And even for convolutions, you know that there are maybe 10 or 20 variants of convolutions that people want to optimize for. As a system people, actually, another thing that I always ask myself is how I can perform high-level system optimization to really get the best performance out of my computation. So one of the things that I might try to do is I will try to actually take this high-level computational graphs and fuse a few of nodes together. The idea is that we can try to fuse two nodes so that there's a fused operator that don't have to store data back into global memory before you compute next computation. Usually, this kind of fused operation can give you 1.5 speed up versus a traditional workload. However, the problem now is that the blue node which is introduced by operator fusion, no longer exists in the low-level library. So what can we do? As a framework builder, actually, usually the only option I have is to give up. Because, and that was the situation that we faced before, and it's really upset to find that we have all those ideas of building optimizations, but we are not able to actually build efficient library to run them. Alternatively, actually, we can try to hire an engineer or a team of engineers to add that library to a low-level library. The problem is that there's a great amount of turnaround time, and not all the engineers are experts in optimizing code. If you want to multiply that by amount of hardware backends that you want to support, you can imagine how engineering intensive that is. So that is the problem that we are faced in nowadays. And that is the problem that we really want to solve by using automated solution. That's why in TVM, we are trying to take a brandly new approach. Well, this is a highly risky but also rewarding one. The idea is that we want to replace this human effort of bridging high-level computational graph to low hardware by an automated system. The system contains two components. The first component is a hardware-aware search space that contains all the possible program optimizations that we might perform. The idea is that the search space is big enough so that whatever optimized program that a programmer or expert might write, we can find that program in the search space. The second part is a machine learning-based program optimizer, where my colleague Eddie will talk more in detail today. The general idea is that we want to combine these two parts of the system so that it can automatically generate code for new operator and workloads and hardware, so that we don't have to ask engineers to really hand optimize each workload and each combination of fuse patterns that's out there. And this will really enable us to do more system-level optimization and building support for all kinds of different variants of hardware backends. So I will tell you a bit more about what is a hardware-aware search space look like. The general idea is that for each of the low-level operations, we'll try to describe them in what we call tensor expression language. This is a declarative language that specifies the computation pattern that we have in here. And in this example, this tensor expression language describes how can we compute a transpose matrix multiplication. TVM have a wide spectrum of declarations besides the compute primitives. If you find, you can hear more talk today about hybrid scripts or other computation that allows us to describe non-regular compute patterns other than this kind of tensor computation. The idea is that we want to build an extendable spectrum of declarations that can cover all the possible computation that you can encounter in deep learning workloads. And then, after we have these high-level specifications, what we really want is to define a search space on how we can map those high-level computations to different kind of hardware backend. We borrow idea from existing image processing language Halide and a few others to separate the compute declaration from the mapping, which we call schedule in here. And the real innovation that TVM brings on table is that we bring a wide spectrum of schedule space that covers the state of art on GPUs and enables specialized ASIC support. So on CPU-like devices, we can perform optimizations such as optimize for cache locality and take benefit of vector instructions that modern hardware have to offer, such as AVX512, that's very important on the next generation of Intel CPU, or Neo instructions that's very important on ARM. It becomes more interesting to support all kinds of hardware backends besides CPU. For example, we might want to support different variants of GPU backend, as well as TPU-like specialized accelerators. So for GPU backend, one of the interesting perspectives is that GPU allows you to explicitly manage what we call shared memory. And usually, you need to have multiple threads to cooperatively manage those shared memories. In order to maximize the GPU utilization, it's important to actually build primitives that allows multiple threads to cooperate with each other and cooperatively make use of shared memory to reduce memory access versus compute. And TVM provides new primitives to actually enable that and get us to the state of art of GPU performance. I think the most exciting thing about modern hardware nowadays is ASICs, or like specialized accelerators. So if you look at the specialized accelerators, one of the interesting perspective is that the compute primitive offered by the specialized accelerators are not scalar or vector instructions, but tensor instructions. For example, traditionally, if you look at CPUs, you can program your things by describing how do you compute each element of that. Actually, this is the simplest way that I can program it. I wish I can always remain that way. But unfortunately, if you look at modern ASICs, actually, the basic compute instructions are tensor instructions. For example, Volta allows you to do a matrix vector instruction. And if you look at TPUs offers you matrix instructions. And because there are so many variants of tensor operations that you can enumerate, you can find that different ASICs will have different intrinsics, both for memory and both for shuffling memory or doing computation. So how can we make our compiler future compatible so that it can be used on all kinds of ASICs that might be incoming? The idea is that we will ask hardware designer to also use the tensor expression language to describe the hardware interface that those hardware might offer. For example, if the hardware allows you to do 8x8 matrix vector instruction, the hardware designer would declare that my interface is this like 8x8 matrix vector instruction using this declaration language. At the same time, the hardware designer will also declare how do you lower the existing expression to the low-level hardware intrinsic. Then, the idea is that TVM will have what we call tensorization path that will try to match and replace the certain regions of computation using the tensor intrinsic. We're also actively working on automating this process so that we can directly take the tensor instruction from the future ASICs and directly transform a program to make use of those instructions. Besides the hardware compute intrinsics, another interesting thing about specialized accelerator is that they have these special memory patterns, such as you need to explicitly load data to the special place of memory before you run computation. And we need to explicitly manage the memory load with compute so that we can overlap computation with the communication. My colleague Thierry will tell you more about how do we do latency hidings and all the other stuffs in the context of Vita and the other kind of ASICs. The combination of all this search space actually gives us all kinds of optimization primitives, including actually we borrow existing transformations from prior works and derives new primitives such as thread cooperation, tensorization, and latency hiding that I just talked about. And if you combine all those possible optimizations, what was happening before is that an X programmer or a team of X programmers tries to pick certain options in this space of optimization and really find the optimal program from this space. And the challenging part is that there are billions of possible optimization choices in here, so that we cannot really brute force enumerate that to get the best operations. And that actually comes to the second part, and where the automation really shines, in the sense that we are using a machine learning-based program optimizer to optimize the performance. I wouldn't dive into detail of this part, and my colleague Eddie will tell you more about how we can do machine learning-based program optimizer. But one thing that I will highlight here is that the design principle of a TVM is we want to rethink how we design modern systems and compilers to bring automation as part of the first principle, so that we can design a system to really take benefit of machine learning and use machine learning to automate what previously done by human engineers. And by doing that, actually, we can really bring portable performance to all kinds of systems. So you're going to see quite a lot of interesting results today, and I'm going to tell you some of the quick results, and I'm going to tell you why this kind of automated approach is important. This is one of the end-to-end inference performance on NVIDIA Titan X. And the y-axis is time, so lower is better. And we are comparing on several benchmarks here. All the baselines that we have here, Apache MXNet and TensorFlow, are backed by CUDM, which is a manually optimized library. This represents what you can get using the traditional approach. And we also show TensorFlow XOA, which is Google's TensorFlow compiler, as a baseline. The first thing that you want to notice is that XOA is not necessarily faster than the standard frameworks. This kind of highlights how hard it is to actually bring an automated solution that to compete with human expert, because this is really a hard problem. If we use TVM, you can find that TVM can automatically generate code without relying on any of the external library that is running faster than existing solution. And as I mentioned to you, because TVM allows you to automatically generate all kinds of code, we can actually do the system optimization that I mentioned. For example, one thing we can do is we can do graph optimization, such as doing operator fusion and layout transformation and so on. And by combining all the high-level optimizations, we can get even faster performance. And this is something that we are not able to do in other frameworks because the restrictions of operator set in a low-level library. If you look at far left, you can find that we're already being competitive on the standard benchmark libraries like ResNet 18. But what's become more interesting is that if you look at the right, this is a deep Q-learning model. This is the model that's used by DeepMind to play Atari games. You can see it's an important model, argument play. There is a 3x gap between the baseline and TVM. Anybody want to guess, like, what's the reason here of the gap? So one of the reasons that you can guess, like, the reason is that most of the human engineers will spend their time optimizing for the public benchmark, such as ResNet. But if you talk to Wang or if you talk to Carlos, they will tell you that their internal customers will always want to deploy the model on somewhat non-standard benchmarks, such as they want bigger image size, they want to deploy a model on self-driving cars, which will have different model characteristics. Those models are not necessarily looked by the engineer who are optimizing them. And as a result, these models are not usually, while human optimized libraries get you the best performance on the standard benchmarks, they don't necessarily get you the best performance on your customer's application. Because TVM uses machine learning automations, the machine are tirelessly optimizing every layer, every operators on the target model that you are interested in. And that brings us this 3x gap from the standard baseline. And that's what we are really excited about, because TVM allows you to enable all kinds of wide spectrum models so that researchers also don't have to restrict their explorations on just what standard library is doing well, and we can quickly deliver new models to the production pipeline. Another exciting thing about TVM is that we can reuse the same solution across wide spectrum of hardware backends. In here, we are showing results on ARM CPU and ARM GPU. You can see that, for example, on the ARM CPU result, we are comparing against baseline, which is TensorFlow Lite, which is not TensorFlow, by the way. TensorFlow Lite is a specialized deep learning system specially designed for inferencing on the edge. As you can see that because the traditional solution requires a lot of engineering effort and manual effort, most systems will have to build new systems for each kind of platform. While we are able to use the same solution to optimize for ARM CPU, and in the case of our ARM GPU, we are able to outperform ARM compute library, which is the ARM's in-house solution, on both floating point and 16-bit floating point, which is kind of non-conventional. Another exciting thing we are really excited about is that TVM is not able to support CPUs, GPUs, and we are also working on supporting specialized accelerators that Thierry is going to tell you more about today. The idea is that we really want to use Vita as well as other special accelerator pipeline as basically a testbed on building optimizations for deep learning compiler, so that the academic and industry can come together to really build a solution that's open source and can be reused by everyone. So far, I've told you a lot about how we can do low-level optimizations and how can we customize low-level libraries, use automation to get things to run fast. Another thing that we are really trying to innovate on is how can we bring more high-level optimization as well. For example, Carlos alluded to you that we really want to be able to bring the end-to-end training loop on the device or on your target. And that really requires us to have a better high-level representation that contains things like a high-level control flow and symbolic shape or things like that to give you ability of doing high-level program analysis and whole program optimization. And we are very excited to bring the PL group in Yida to work together with the TVM community to bring this high-level IR relay to really give us more end-to-end whole program optimization. And you will hear more about Jerry today on talking about relay today. So as a result, TVM is a learning-based deep learning compiler that combines different components, including high-level differentiable IR, the low-level tensor expression optimization, targets different kind of hardware backends, and more importantly, have this end-to-end automation stack that gives you the end-to-end performance automatically. I would like to emphasize again on the way that we do open source, in a sense that TVM really tries to become an open governance model that really try to push forward the open governance model that allows everybody to come contribute and work together as a community. As an example, usually we will prefer publicly archivable discussions, and most of the major features will start with the open RFC discussion. You can find the community guidelines in the following link that will tell you more about how we run the community. We actively bring new members by the merit of their contribution. So on the right, there's a screenshot on basically bringing new reviewers and committers to the group. We have committers over all the continents. For example, recently we bring Masashiro, who is from a Japanese startup. He's using TVM in his company, and he contributes a lot to the AMD and Intel CPU backend, and he's now a committer of TVM. And we are also having new reviewers, Andrew, who will talk about Facebook's effort today, and we are really lucky to have this wide spectrum of collaborators to come together to contribute and work together as a community. And we really think that being open and collaborating in the public is really one of the key sources of moving forward and bring the community together to get the state of our next stage compiler. So yeah, that's it. Throughout the course of today's talk, you will hear more about each component, and I will be happy to take some of the questions, but other than that, we can bring the next speaker on board.
We have time for questions. Yeah.
Okay, sounds good.
Thank you. So my name is Kiran. I work in Western Digital Research. Thank you again for your presentation. So when you compared in terms of the benchmarks, did you have a chance to compare with the TensorRT from NVIDIA that is well optimized compared with the others?
Yeah, so the question is like, how does TVM looks like comparing to NVIDIA's TensorRT compiler? If you go to tvm.ai blog post, there's a recent blog post actually comparing against TensorRT on floating point performance. And you can also find that TVM is already getting on par with TensorRT, which is actually NVIDIA's best effort. We are quite excited about that result. Yeah.
This is Yida from Amazon, working close to the TVM community. So regarding the benchmark you mentioned, is it based on Relay or NVM v1?
Can you say that again? What?
The benchmark, is it
benchmark.
based on?
Yeah, the benchmark is based on Relay, actually. So far, what we found is that Relay already gets to performance feature compatibility with NVM. So all the features that you have in NVM v1 is already available in Relay. And Relay also have actually new features. For example, the high-level operator fuser is more powerful than what's being offered in NVM.
Hey, could you please elaborate a little bit more about your open source strategy? So far as I understand, you have like a project on GitHub with Apache license, is that right?
Yes.
So do you plan to be part of the Apache Foundation and so on?
Yeah, so that's a great question. So the question is like, what is our open source strategy? So far, TVM tries to adopt Apache governance model, and you will actually hear more about, there's ongoing discussion on possibility of incubating TVM. We will have an invitation on Marcus Weimer, who will be talking about today. Yeah.
At the end of the day.
Yeah.
So say your thoughts, and let's open that session.
Yeah.
All right. We have a question. One more.
Hi. For those of us who are, let's say, bringing up teams or getting people to work on TVM, what would you say is the most efficient, fastest way for somebody to get familiar with the TVM expression language?
The question is like, if you want to work on TVM, what is the best way to get started? So far, TVM have somewhat okay form of documentation on how you can get started in terms of developer document. If you find that there's something that you need, do ask questions in the developer forums. The forum is actually quite active. And you will find like developers, both from Yida, Amazon, Huawei, Facebook. There are a lot of people there who can answer your questions. The general idea is that we want to bring all the discussions and development in the public so that everybody can contribute and collaborate, and you can see the progress on what's going on. Yeah.
All right, thank you again. Okay, so context switch here. So while your context switch, I wanted to mention briefly about this venue. So this venue is called Intellectual House, and it's actually dedicated for the Native American and Alaskan community to get together. There's a bunch of community events here. And you know, this is finals week on campus, so this is why this is the only venue available. But the condition is that everyone has to take a final at the end of the day. So I hope you're all paying attention. You know, there will be a final that the 4 faculty sample, you know, put a lot of effort in putting together. You can also replace that with a check too. So that's the last time I mentioned this, by the way. With that, let me introduce Yida, Wang from Amazon. He's going to be telling us about his efforts of deep learning compiler optimizations at AWS. So.
Hello, everyone. My name is Yida Wang from Amazon. Thanks for having us here. So I'm excited to be here to share with you about our deep learning compiler work at Amazon. As you just saw, I will start with acknowledgement. So the work that I'm going to present is from our team. We have a large team here working on deep learning compiler and other stuff. And so the credit goes to every single person in the team. So a couple of weeks ago, we in AWS reInvent, we announced so-called Amazon SageMaker Neo. This is to enable the developers to train machine learning model once, but you can run them everywhere on the in the cloud and at the edge. So we do this because, you know, we are Amazonians. We work backwards from the customers. So we understand that this is in great need of our customers to run different machine learning models on all kinds of hardware. So we have our hardware targets listed on the left, and we have a lot of ongoing and potential customers, both internal and external. And as you know, part of the machine learning model, the major part of it is the deep learning model. So on the deep learning side, we work on TVM. We love TVM. We are proud to participate in the very beginning of this project in the open source domain, and we are always being a group of the major contributors in the community. So in Amazon, you know, we build products around TVM for deep learning compilation. On one hand, we work as part of the open source community to improve, to add new features in the core TVM features. And on the other side, we also work on products. So we work on more comprehensive support for building a product. So for example, listing in this slide, you can see that on top of TVM, we currently, as part of Amazon SageMaker Neo, we support TensorFlow, MXNet, and PyTorch. So for example, you know, we figure out that on the PyTorch domain, the operators of PyTorch, if you go through ONNX, there may be some issues. So we work with the PyTorch team to make the PyTorch graph as a symbolic graph so that we can take it from there to feed it to TVM. And also, you know, at the bottom, you see we are supporting different the chips from different kind of chip makers, also including our own chip. So in order to make sure that the support is comprehensive and reliable, we are building our nightly test to run on different kind of, for example, AWS EC2 Amazon EC2 instances and other like devices to test out the accuracy and the performance of the compiled module that we can get. And also another example of building a product would be, just last night, Jenny sitting here submit a new issue to the open source repo talking about making a more comprehensive and formal error handling mechanism for the entire software stack. We think this is important for us in terms of engineering. So today I'm going to talk more about the core features that we add in to the TVM community. So, as Vin just mentioned, we participate in a lot of the feature building, but I just would like to select some of them, mostly be the features that are led by our people at Amazon. So the first thing that I would like to talk about is about conv kernel tuning. So everyone knows convolution is the most important operator in the CNN models. So we are working a lot on tuning the convolution kernel for different kinds of devices. So today I'm going to talk about two devices, both from Intel. The first one is the Intel CPUs. The reason of doing this is everywhere. So it's very universal, available in a lot of places. The people are doing a lot of inference on Intel CPUs. So we take the Intel CPU on cloud. In the cloud, as an example, this is Skylake CPU, still the latest one. So it has like multi-cores, it has AVX 512 support. So you can, if you want to get good performance out of this device, you need to leverage all these kind of features. And people can do it in multiple ways. As Tianqi just mentioned, the conventional way of doing this is you just do it manually. So, the TVM can do similar things, just basically the same thing in a much more convenient way. So, for example, first of all, we all know if we want to optimize on convolution, you want to make sure the data layout is favorable, is friendly to the hardware. So people know that there's some general effort. We just change the NCHW format into NHWC, and we also divide the last dimension, the channel dimension, into chunks to make the convolution into 5D, so that this would be more efficient on the Intel CPUs. And this is easily done by the TVM domain-specific languages I just listed on the top. So the other thing to run convolution efficiently on the Intel Skylake CPUs is to utilize the AVX 512 instructions well. So by doing this, again, conventional way is you go to intrinsics or the pure assembly code to write it properly. And in TVM, it's easier. We prove that you can use the TVM scheduling schemes to try to, once you understand the compute architecture well, you can try to use the the scheduling scheme to construct a good template of convolution of the convolution computation scheduling, so that together with the auto TVM that I think Ed is going to present later, so we can easily get great convolution performance out from the Intel CPUs. So the next hardware targets that we are working on is the Intel graphics. The reason of doing it is we think this is the most underestimated device that you can do great deep learning work. So the Intel graphics is actually also everywhere, is on this laptop, for example, but not very many people are paying attention to this device. So if you look into the architecture of this device, it's vastly different from Intel CPUs. The cores are organized into EUs, and you would need to make sure that you are utilizing its memory hierarchy well, like it has its register files and onboard memories, and eventually go to the main memory. If you write it naively, utilizing all the data, like getting all the data from the main memory, the performance is going to be terrible, and I think this is the main reason people are not using it. However, in TVM, we can make the utilization of the Intel graphics much better than the knife programming, and it's also easy. We developed the core features of TVM to support the Intel graphics in terms of subgroups. So the subgroup is just a concept in Intel graphics that the work items in one subgroup, you share the same register file. If you make sure that every compute chunk could be allocated to one subgroup, the memory utilization will be much better. You will be enjoying high memory bandwidth and getting good performance out. So doing when we do the convolution, we first leverage the data layout trick that I just presented in the Intel CPU part, and also pay attention to using the Intel graphics subgroup. And again, by doing this, we can generate some kind of template, and together with Auto TVM, it's easy to get good performance out of convolution in Intel graphics. So the next part of the features that I'm going to talk about is more on graph level. So just now I talked about some tensor level optimization. So on graph level, we also, based on TVM, we also did something to improve the performance. The first thing that we have done is to do graph level layout optimization. The reason of doing this is if you think about a CNN model. Like just now we talked about convolution, we know data layout of convolution is important, but the thing is if you only treat the convolution as an independent op, you do the data layout transformation within this convolution, but this would not be a good idea if you extend your view to the entire network, because if you do the layout transformation for one convolution, then you have to redo the similar thing for the next one. This is going to give you a lot of overhead, unnecessary overhead. So the way of doing is from the graph perspective. How would you coordinate different the data layout of different convolution to make the to remove the unnecessary data layout transformation? And another thing to do is for the convolution kernels, since you are transforming the data layout of the convolution, the layout of the kernel should be translated as well, should be transformed as well. So in this part is in runtime is invariant, so you can actually do it in the compilation time. And we add a new part called alter op layout into the TVM repo to take care of this part, so that we can remove the unnecessary data layout transformation to make the entire performance better. And the other thing that we are doing is so-called graph and tensor optimization. So from this diagram, you can see that if you want to have good performance on each single convolution, you may need to add in some kind of layout transform in between. So this layout transform gives you overhead. Sometimes it's worthwhile paying, sometimes it's not. So how to decide this? You want to look as a whole to summarize the time it takes in every convolution, and plus the time it takes in layout transformation to see if you want to pay this additional layout transformation overhead in yellow or not. So in order to do this, we can do it in a brute force way, but it's going to be intractable, as you can imagine, once the structure of the graph is a little bit complex. So we utilized some kind of a dynamic programming trick to deal with the problem, but this sometimes might not be enough. The dynamic programming could be still intractable applying to more complex networks like SSD. So in this kind of case, we are also investigating the direction of adding in some kind of necessary heuristics to make the search more intelligent and get reasonable results out. So I'll just show with you some quick end-to-end results. This is on some classic CNN and object detection, or CNN models on Intel CPUs and Intel graphics for inference on the batch size 1. So this is actually measuring the latency, and it's this is the speed up, so the higher is better. You can see that we are basically working at least similar as the benchmark results that done by the chip vendor using the conventional way. And sometimes you can see that we actually not outperform much. That's because we are also actively updating our benchmark result. We are trying to get the most respectful baseline instead of getting some random thing to get 10 times speed up. And the other thing to emphasize here is in using TVM, it's easier to get good performance out, as Tianqi just pointed out. If you have a less conventional model, you may get more speed up. And the takeaway here is using TVM is easier to get performance out, and it's a more generic and flexible solution that you can get. So next, I would also like to talk about some other functionalities that we add into TVM. We just pick some of them. So the first thing that I would like to talk about is a runtime multi-threading pool that we add into the TVM to the CPU TVM runtime. So the way that we do this, we use a customized thread pool to implement the parallelization. So some technical details here, like we use lock-free queue, we bind the thread to physical cores. We also use some cache line padding to make sure we get rid of the false sharing between different threads when accessing the global data structure. And the reason we do this instead of using the off-the-shelf ways like OpenMP is because in our experiment, we found that in this kind of almost embarrassingly parallelizable tasks, the OpenMP result is not that good for some reason we may not know. And then also, using OpenMP, you are adding one more dependency to your project, to your repo. This is not favorable to us as well. So we decide to use our own, and we compare our own thread pool with the framework solution, the OpenVINO solution, and even our own solution, but just replace the thread pool with OpenMP. And you can see that we can get the best scalability out for different kinds of models. And the next thing I would like to talk about is we call it graph annotation. And the reason of doing this, if you look into for example, if you look into the current SOC system, you want to run some kind of framework on for example, your mobile phone. So most of the work will go to GPUs, but sometimes you find that some of the work is not well taken by GPU, and you may want to fall back to CPU. So how would you do this in TVM? So we propose that you can do this by annotating the nodes of your graph into, in this case, CPUs and GPUs, and add, in the second column, you can see those small data copy node. Add a data copy node between different devices to make sure that you will be able to transfer data between different devices. And then this is more engineering work. You can compile the code into generate code on different devices, into this case CPU lib and GPU lib, and then in the runtime, different node would be able to find its own implementation into different libraries, but all the things are still within the TVM runtime to make this transparent to the user. And one more thing that I want to mention is about the quantization. Everyone knows this is important, and this is just some early attempts on the Intel's on Intel CPUs. So as you may know, the Skylake, Intel CPU Skylake in AVX512, they provide some 8-bit and 16-bit instruction that we can utilize to run int-A operation on neural networks. But this is far away from complete because there's no LLVM support on this, so we have to write out our own intrinsics and tensorize them to make use of these instructions, and also the instruction set itself is not complete yet. So, and we are looking forward to the next generation of the Intel CPUs for solving this problem, and we are also interested in working with the LLVM team to make more like comprehensive support from the LLVM side to support the Intel int8, the low bit instruction compilation. So these are some like quick results that we compared our quantization with the FP32 results. And by the way, all the code that I just talked about, they are somewhere available in the TVM repo. We are the active participants of the open source projects. We are we are willing to upload the code to the upstream. So last but not least, I would like to speak a bit about our ASICs. So Vin just mentioned we announced AWS Inferentia several weeks ago, also in the AWS reInvent. So we believe, those so-called AI chips or ASICs will be a very interesting direction in the future, and we are investigating into this direction, working with the Inferentia team on building a tool chain with them. And in addition to this, we are also interested in looking out to see the ASICs provided by other companies, as well as the Vita architecture that proposed in the academia field. And we are, that's something that we would do in the future. So eventually, some quick takeaways. First, industry needs, we believe the industry needs an open standard compiler for deep learning, and we, Amazon, AWS, are working on the TVM stack. Secondly, we are eager to collaborate with the community. So we have 10 plus people here today. We will proactively reach to you to talk, and also come to talk to us if you are interested in anything. And last, as I just want to echo Vin's top right corner, we are hiring. So, from the scientists to engineers to interns, if you're interested, talk to us, write to us. Thank you, that's it.
I saw FPGA as one of the targets in one of your slides. I'd love to hear a little bit, whatever you can share in terms of what you guys are doing to support FPGAs.
We are talking to FPGA companies like Xilinx to figure out if there's a way that we can utilize TVM on top of their hardware targets, and working on, for example, AWS EC2 F1 instance. So that's something that we are working on.
Is the idea to generate Verilog directly, or are you going to have a template design that you... Is the idea to generate Verilog directly?
It's still under discussion.
Great. Any other questions? Yes.
Hi, thank you again for a good presentation. So on the FPGA side, I have a follow-up question. So there are two implementations. One is XDNN. Then there is another one called DeFi implementation that is more similar to NVIDIA DLA. So which one you are targeting on the FPGA side?
You mean the FPGA side?
Yes. Yeah.
Again, still under discussion.
Okay.
We do not have a concrete plan on that yet.
Okay, thank you.
All right, yeah, one more, and then we'll take a break. Yes, please.
For the Inferentia, the chip, when do you think you will make it available? And are you going to make it public available?
It's going to be available, I think, late 2018 as delivered by NDJC in the keynote. And so for other things that, I guess, refer to the keynote would be the most official place that I can provide. Yeah.
All right, let's thank Yida one more time.
Thank you.